Fault finding, lesson 4, hazards of fault diagnosis. In this lesson, we'll try to understand the hazards of fault diagnosis and we'll try to understand the electric shock path. We'll also look at what to do in the event of electric burns and we'll discuss the causes of arcing and explosions. As we've discussed in previous lessons, fault diagnosis is high risk due to unknown issues causing the fault. In order to work safely, the person or people performing fault diagnosis work must first of all understand the hazards of fault diagnosis and how those hazards can be minimized. They must also be able to work safely and follow a logical procedure as required. They should have a good understanding of the types of faults that may exist. This can only come with experience and learning combined. They must also know how to use the test instruments and correctly prepare them for the required test. And finally, they must be able to interpret the results and data that they have collected. The electricity at work regulations require those in control of an electrical system, that is, the responsible person or the duty holder, to ensure that it is safe to use and that it is maintained in a safe condition. There are more than just electric shock hazards associated with fault finding. Some of the other injuries that can happen when a person comes into contact with live parts includes electrical burns, loss of muscle control, fire, arcing and explosions. Answer the following questions based on the previous slide using your own words. If you struggle to answer any of the questions, go back to the previous slide and watch the video again. You'll notice that resistance and impedance are used interchangeably at this level, but there is a difference. The only thing that has resistance only is a resistor, and this resistance will remain the same when a DC supply or any frequency of AC is applied to it. Everything else that conducts a current will have some level of inductance and capacitance, however small that may be. This means that if an object has impedance, its overall equivalent resistance will change based on the frequency of the electrical supply. In the UK, the supply to domestic premises is 230 volts single phase at a frequency of 50 Hz. At this level, the average person has a body impedance of approximately 1300 ohms. Based on these numbers, 177 milliamps, that is 0.177 amps, will be able to flow through a person during fault conditions. That may not seem like much, but only 50 milliamps, that's 0.05 amps, can be fatal if flowing through the body for only a few seconds. Electric shock is caused by contact with live parts. This usually happens when basic protection is missing or damaged, allowing direct contact with live parts. It could also happen by indirect contact. This is when fault protection is missing or it's inadequate, exposing people to shock from parts that have become live during a fault. There are occasions when poor installation practice may expose bare live conductors at terminations, creating a hazard. In some situations, exposure to static electricity may cause a significant shock when the static is built up over time during a high-speed industrial process. A less common but still important hazard to know about exists when the cracked case of an electrical device is subjected to moisture. This can allow electricity to flow on the outside of the insulating material that is used as basic protection. When this happens, it is known as tracking. Answer the following questions based on the previous slide using your own words. If you struggle to answer any of the questions, go back to the previous slide and watch the video again. The magnitude and duration of the current are the two most significant factors when considering protection. This is why we check both the tripping current and time it takes for RCDs to trip. The magnitude of the shock current depends on the contact voltage and impedance of the shock path. Remember that a current as small as 0.05 amps can be a risk to life, but this current cannot flow if there's not sufficient voltage to push it through. The ground shock path is the most common. It starts at the point of contact with a live part. It travels through the body to the ground, usually through the feet, but this is not always the case. The current then travels through the ground to the distributor's earth connection and back to the supply transformer. From here, the fault current passes through the supply transformer windings and back down the line conductor to the point of fault. In this case, the shock path impedance is the body impedance plus the external fault loop impedance. A more dangerous situation is the hand-to-hand shock path. In this case, the body becomes the load for the circuit. This happens when one hand is in contact with an exposed live part and the other hand touches a different live part. This can be either the neutral conductor or even worse, another phase conductor. This would expose the person to a significantly higher voltage. The current in this case will only be limited by the impedance of the body. One test that is performed is the prospective fault current test. This shows the amount of current that can flow in fault conditions, and this is regularly in the range of thousands of amps. One safety measure that is used is installing an extra low voltage system. That is 50 volts AC or 120 volts DC. At this level, the risk of electric shock is reduced, since the lower voltage cannot put 50 milliamps through the body, and any arcing is not likely to develop enough heat to cause burns. People who experience an electric shock often get painful muscle spasms. These spasms cause loss of muscle control and can even be strong enough to break bones and dislocate joints. The loss of muscle control can also cause a person to tense up and hold on to the live part, maintaining that electric shock. Direct current particularly locks a person's muscle, preventing them from letting go of the conductive part. However, there's no impedance with DC, so the resistance of the body may be reduced with AC, causing a larger current to flow. That is why 120 volts DC is considered safe, while only 50 volts AC is considered safe in extra low voltage systems. Another hazard of electric shock is that a person may fall if they are working at height, or an explosion could cause them to suffer burns and be thrown into nearby equipment. Answer the following questions based on the previous slide, using your own words. If you struggle to answer any of the questions, go back to the previous slide and watch the video again. A person may suffer an electric burn injury in a number of different ways, and each one will have a different effect. Firstly, a burn may happen as the direct result of a current passing through the body at high voltage, or a bright flash from arcing current can expose a person to high frequency radiation, or also it might just be the result of direct heat of the current passing behind insulation. In this case, it would be a common surface burn, but if it is due to the current passing through the body or radiation, then the burn may not show or might appear to be minor, but it can extend deep into the tissues behind the skin. If this is the case, you should always seek medical attention. Many fires in domestic premises are caused by electrical distribution. In general, this is due to overheating or arcing when one or more of the following faults occurs: insulation failure, overloading, that's switches, isolators, conductors, a lack of electrical protection, or poor workmanship or design. And incorrect storage of flammable materials will propagate fire after it is started. Answer the following questions based on the previous slide, using your own words. If you struggle to answer any of the questions, go back to the previous slide and watch the video again. Arcing occurs due to short circuit flashover caused while working on live equipment. That is when two conductors with different potentials or voltages come close but do not touch. The resistance of the air is not enough to prevent the current from flowing, and so it jumps through the air like a small lightning bolt. In some circumstances, this can cause an explosion due to the ignition of flammable gas vapours or liquids in the atmosphere. For this reason, some places like petrol stations will have special arrangements for training and tools and equipment that can be used on site. When arcing happens, it can generate extreme heat, burning the contacts. It will generate UV radiation, which can cause severe sunburn, and if enough current flows, the heat will be enough to cause molten metallic particles to fly out onto exposed skin. Answer the following questions based on the previous slide, using your own words. If you struggle to answer any of the questions, go back to the previous slide and watch the video again.